Brief little tiny note as to, first of all, what is resolution upscaling. So resolution upscaling, well, let me get all intimate with you and tell you about resolution upscaling. Resolution upscaling is the idea that you can, and then I can move this back down again. The idea that if you have an image of, so you might have an image that has various levels of dark and light in it. Something like this. You get a small set of pixels like this that have various tones to them. And an upscaler, first of all, let me talk about the generic idea of an upscale. And then let me talk about, in specific, what is exciting about a lot of the stuff that NVIDIA is doing. So the idea with the upscale is that you want to turn these 4 pixels into these 16 pixels. But what color should you color in these 4, say? Actually, let me just mark with red. What color should you color in these 4? So obviously, a stupid thing to do would be to go, oh, these are white, and then these are oh my god, classic MS Paint problem. Oh, these are gray, because you're translating it over. But the idea of a upscaler is that there is some algorithm, there is some methodology by which the computer takes this input data and outputs maybe something that looks somewhat like this. Maybe see, this is a lighter color, so maybe we do something like, we smooth it out maybe some way like, oh, not like that, Swear to God, I need to just close this link, don't I? There we go. Oh, that feels good. That feels good, doesn't it? Come on. I want this example to actually be good. So the idea is that you might have some image like this highlighted in blue on the left that goes through, again, some algorithm in order to generate this image. So for a while when there was resolution upscaling, you'd actually have you have a mathematician sitting there going, let me see, what should be the rules that would cause this low resolution image to become a higher resolution image? And in what circumstance would you want low resolution to high resolution? Maybe if you took a photograph of someone really, really far away and their face is only a few pixels, it would be nice if you could just kind of smooth that out and make it a little bit more of a face-looking thing. Well, through the use of machine learning, basically the idea of any machine learning algorithm, okay, let's make this black, let's move this over. The idea behind any machine learning algorithm is basically the following. So you have your inputs that get fed into the brain. Not official terms. Normally this is written as G of X, but whatever. Brain. And then you have outputs. Then you have this separate thing that has many, 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 many names. But it is the reward equation, the loss function, reward function, loss function, advantage function. There's some way. Okay, so I'm going to draw my wiggly line. So let's ignore this half for the moment. Let's ignore this half. You take the input in, the brain will do some processing, you'll have some outputs, and what this reward function is it's basically some way to say, how good or bad did you do at the output? So a really common one is you take in pixels, and then you have a brain that does some processing, and it outputs whether the number that the pixels represent is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And the idea of the reward equation, the reward function, is saying how good of a job did you do at guessing. That version that I just gave, take in pixels, put out 0 to 9, has a very simple reward function. You get punished, you get a negative reward if you guess the number wrong, you get a positive reward if you guess the number right. Now, what's really interesting about this is, well, I'm realizing I'm skipping some steps. So typical machine learning is it's going to compare the output to what the correct number is and either get rewarded or punished based on that. And then using the reward or the punishment, it will adjust the brain in some way. It's going to adjust the brain in some way. So take a moment to think about how you would normally do traditional coding algorithms, right? You know, like if you were a statistician trying to detect whether or not fraud was happening, there would be a person who would be programming the evaluation process. Machine learning is very different in that you just carefully sculpt the inputs, carefully sculpt what the outputs are, carefully sculpt what the reward is, and then you let this brain just update itself again and again and again and again and again and again and again until it's good at making this output match whatever you're rewarding it against. And so the thing that's interesting about this is that the whole point is that I don't have to figure out the algorithm behind it. However, the algorithm is what we care about. And so, in other words, whenever you see a machine learning algorithm producing something good, we don't actually know what its evaluation process is or why it's so good, because we didn't write that part. We only know that the distance between what we want and what reward we're going to give it becomes very, 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 very small. It gets better at doing something that rewards it. And so, what's interesting about the idea of this upscaling process that I'm looking at on this left side is that typically with upscaling, when you would write algorithms to try to take a small set of pixels and render it at a large set of pixels, what this would do is it would basically require someone to code the algorithm, figure out exactly what they want it to do. And you'd wind up with a lot of corner cases that looked weird in the upscale. You'd wind up with, you know, some weird things where the human, just by virtue of some corner case, this happens. And you look at that and you just go, that's wrong, right? You just immediately go, that's fucking wrong. And so you wind up with this extreme fragility when a human is behind the wheel. But what's amazing about taking upscaling like this and using machine learning is that we can take an image in control, or in a game, we can render it at a low resolution, and we can render the exact same image. Actually, let me do this. So let's imagine this. Let's imagine this is, let me label this low. This is upscaled. Forgot the A, upscaled. High. So let's say here's a low pixel resolution image in our game. Let's say this is a high resolution pixel image in our game. It's actually very easy to take these two pieces of data in red, feed the low resolution one in to a machine learning algorithm, let the brain produce what it thinks is an upscaled image, and then you compare the upscaled image here, which would be this, you compare it to this. In other words, the hardest part about machine learning is figuring out how to set up this, how to set up these, and how to get enough data. But when you're doing graphical technology, it's trivial to generate the data. You just generate the low resolution one, you generate the high resolution one, and you make the brain learn how to turn low resolution into high resolution accurately. And then you throw trillions of images at it, let it learn multiple trillions of times over those billions and trillions of images, and then it starts to get really good at the upscaling. Now, what did I draw? I drew this low resolution image being upscaled to this resolution image where it goes from light to dark in this sort of gradient, and maybe this is actually what it was. So, you wind up with some inaccuracy. You wind up with some sort of problems with getting things perfect, but you don't really care. You don't really care that much. Definite velocity. So what's in the brain is unknown. Yeah, actually, if I take the brain and expand it out, what does the brain look like? It looks like little nodes like this that contain numbers in them. So I'll write whole numbers, even though they tend to be between -1 and 1. You have these numbers. Let's write 1 like this, that get fed through various connections of dots and lines. So what happens is the input numbers, let's say these are the inputs. So on each one of these edges is some number. I'm just going to write n. They're all different numbers. But you have these little numbers here that see how this 3, we draw an arrow across to this one? This means take 3, multiply it by n, take 2, multiply it by some different number, and then add these together to be the new sum that we'll call x. Now, and what happens is what these values are get adjusted up or down based upon the learning. They get adjusted up and down based upon what learning is going on. And the reason it's hard to understand what the logic is that how many of these are there? 100,000. How many of these are there? Another 100,000. I've drawn 1 layer, 2 layers, ... 3. Actually, we would say n plus 1. How many layers are there? It's like 40. And how many connections are in between these? Well, that's 100,000 times 100,000 per layer. So, and so this is what makes it tough to see, is that we tend to think in things like 2 rules with 4 corner cases. So this is why it's quite challenging. But the thing is, how do you take this set of numbers and multiply it by this set of weights to get this next set of numbers in this network? It's basically, it's just vector math. It's just large-scale matrix multiplication. And so, the NVIDIA GPUs are very, very, very good at doing parallelizable tasks. And there's certain hardware that you can make that's very, very good on at doing specifically matrix multiplication. And so when you use a GPU that has the hardware that's good at matrix multiplication, and it is parallelizable because it's machine learning, then boom, you have something that is perfect for machine learning. Caleb Gilbert says often they'll be convolutional, which cuts that number of connections down to like maybe 9 times. Yeah. Convolution is a way to reduce. My understanding is that there's a piece of tech called a transformer head that basically makes obsolete convolution, and I might be confusing a transformer head with something else. But I remember Oriol Vinales was suggesting that convolutional neural networks convolution as a methodology in the networks become obsolete. Clark Relisa says, accurate except at the fully connected part. That's a really smart thing about different architectures, how to have less connections. No, I'm going to disagree, because I will say that my explanation is the most fundamental raw version, and the idea of eliminating connections to avoid excessive computational time is an optimization that people have done, which I hadn't had the opportunity to bring up yet, so take it back, Clockwork Elysis. But that said, Clockwork Elysis is absolutely accurate. And so, coming back, so what did I do? I just spent a little bit of time talking about this is what the brain looks like. It's a whole bunch of nodes and edges and numbers being multiplied in gigantic matrices together. And then you just keep updating this network based upon, ooh, I think that this is a good upscaled image. Oh, that was bad? Update all the numbers. Try again. Do we do a good job? No? Update all the numbers. Hey, we did an okay job. We don't care. Update all the numbers. But maybe not as much because it was okay. Not terrible. And so what is interesting about upscaling, again, is that the hard part in machine learning is taking inputs, figuring out what your inputs are, then figuring out what your outputs are, how to reward or punish your brain with respect to learning. And most importantly of all, how do you get enough data? And again, in computer graphics, if you're trying to machine learn, train a brain to be really good at upscaling a game, you can trivially generate the low resolution input. You can trivially generate the high resolution input for the exact same frame and use that as the basis of comparison for this. And so what's also really... Oracle says, how are the updates determined? Random. It uses partial differential equations, which is a very complicated way of saying, because again, these outputs are going to be nodes with, lines coming out of this. And basically, what you would do is you would have some way of determining a number of your badness, a number that dictates what the badness is. So if you can produce a number that dictates what your badness is, the question is, how much do I have to change this to make that badness number go down? And if I have to change this to make this, reward improve, then that means I'd probably have to change this. And if this changes, I have to change this. And if this changes, I have to change this. So at each step, you are essentially asking the question, how much do I have to change myself? This output node, how much do I have to change myself to make the reward better? And then everyone before me matters in that case. And the idea of taking the effect of trying to improve and going back and just updating things in a very basic way, in a very, very basic way. It's actually extremely, extremely basic. That is called backpropagation. And as a sort of just interesting note, a lot of times you will see this. You'll see, let's say, you'll see the correct thing that you want the thing to get minus what the output was, and you'll take the difference between these, but then you'll square it. You know why squaring is done a lot? Well, for one, it means that the number is always positive. But for two, taking the derivative of something that is squared, you will recall, is if you have the x squared and you take the derivative, this is 2x, and you have something that's very easy to compute. And so if you're doing backpropagation, which again, if I say, how much do I have to change the result in a better way? Change is typically you use derivatives in order to deal with change. And so squaring things makes your derivatives easier. That's part of the reason why there's a lot of squared functions. And also, someone just mentioned that each individual studio produces the DLSS. In other words, the deep learning... I assume DLSS is deep learning screen scaling. I don't know what else it would stand for. But the NVIDIA DLSS is custom per game, which is brilliant. What NVIDIA does is it basically just says, all right, we're going to give you a really stupid brain, a basic default brain, but we're going to give you all this architecture in the box, and all you need to do is pump low-resolution images in here, pump high-resolution images in there, let it train for a fuckload of time, and now you have a custom-built screen scaler that's perfect for your game. Oh, it's deep learning super sampling? Yeah, that makes sense. Super sampling is... yeah, it seems fine. And people are interested to know what prompted this. One simple thing, actually, let me just leave this alone. What prompted this is I have this NVIDIA DLSS. DLSS uses AI to boost frame rates for RTX, GPUs, effects available render resolutions. So what I'm doing is if I turn this on, you'll notice my render resolution is 1280 by 720. I'm playing on 1080p, and it just made me go, oh, this is maybe an interesting opportunity to discuss how machine learning is actually relevant and used in this regard. And what's the pragmatic reason? Rendering 1280 by 720 is, I think it's a quarter as many pixels. I think it's a quarter as many pixels. I feel like I'm totally fucking correct. Am I totally correct, or am I an idiot? There's a ratio of 1 to 4 somewhere in the math that I can't remember. No, I don't remember what the ratio of 1 to 4 is. Why it's floating around in my head. Let me see. All right, 1920 times 1080 divided by 1280 times 1280 divided by 720. Let me use parentheses. 1280 is 2.25. You know, this happens to me a lot. I don't remember a lot of number facts. So the number 4 is floating around in my head somewhere. And I don't know why. Doesn't fucking matter. It doesn't fucking matter. Ignore the last 30 seconds. Why would I want to render at a lower resolution? And use this DLSS? Well, because computationally, as I've just learned, there's about half as many pixels in 720 as there is in 1080. And that just frees up the shit out of a lot of fundamental resources on the computer. And then GPUs are very, very efficient at upscaling. And the efficiency gain, basically the amount of computational intensity to render at a lower resolution and upscale, is less than simply rendering at 1080p. The reason the number 4 is floating around in my head, and the reason I have some knowledge about this, is I streamed for 2 years before Twitch existed, and you had to like learn a fuckload about which resolution on the canvas compared to the output led to various artifacting and all this sort of stuff. So let's do this. Let's just try this out.